Yeah. Hi, Shara. How are you?
Hi, Cecile. I'm doing great. How are you guys? And welcome to the quantum photonics room.
Yeah, we're just pinging some more people in. So, yeah, please ping people to come to this room. And I don't know, Shara, if you have some link that you would want to pin at the top.
Yeah, I thought this like chill talk. Since it's a hangout room, so I didn't prepare any reference, but I can easily search for something. If we goes to some deeper topics. So welcome everyone to engage in the discussion. So hopefully we can talk quantum technologies from easy and simple angle. And feel free to ask or share your opinion even you are new to the field. So we are here to try the best to help you to guide you the directions. And also, if you want to share the interesting technologies in the field, feel free to do so. So we are glad to have you here.
Yeah, so we organized this room because we thought that in the past, well, yeah, last year and early this year, almost every day, you will be getting news about what's happening in quantum technologies. That it's becoming quite exciting, although it's still questionable as to when we can, for example, scale up to a significant level quantum computing. And those who are working in the field would say that they are having some kind of estimate of about 5 years, or a target of about 5 years to scale up. And but of course, we are seeing a lot of technologies and a lot of investments that's being done in this field every day, and these are big investments. So there is a lot of excitement that's being created in the quantum world. So that's why we come here today to have a hangout, to have a free discussion, and some update as to what's happening in it. So yeah, please ping some more people in, and we will start shortly. Shara, how shall we go about it? Shall we talk a little bit about, just a little bit about the technology, and then later on, I have some important news to share.
Okay. That sounds great. I thought today is a hangout room, so I didn't prepare anything. But I can talk about the topic in general. It's really a big topic, so I'm the expert. But I hope the experts in the room can join the discussion and maybe correct me if I said something wrong. So since we talk about quantum technologies a lot, but what do we mean when we really talk about quantum technologies? So basically, the quantum technology is a emerging field of physics and engineering. I would say it relies on the principle of the quantum physics, quantum computing, quantum sensors, quantum cryptography, quantum simulation, quantum metrology, and quantum imaging. They are all examples of quantum technologies. So it's really a big topics today. But all these different fields, they all have the same property of the quantum mechanics. Especially here, we are talking about quantum entanglement and quantum superpositions. And for some applications, we even talk about quantum tunneling. So why this technology is important. Another question is why we are here to talk about this technology. I think actually it's not new. It's not something new for the quantum technology. If you look at the history of the quantum physics, you would see the quantum revolutions actually started like even like one century ago. So maybe I would call that as the first revolution of the quantum technology. So which I mean, in the past one century, so we basically did lots of revolution in atomic or the subatomic physics, so which gave us some very popular technologies. Like nowadays, that's the reason why we have the iPad and why we have the semiconductors, and why we have lasers, and even why we can do the MRI, the magnetic resonance imaging, and even we also development of very precise atomic clocks. So all these fascinating technologies are all based on the quantum physics, but they didn't use the full power of the quantum technologies. That's why if you search some articles, they probably will see something like the second quantum revolution. So what does that mean? So I guess in the second quantum revolution, people will think about the quantum mechanics not only to be applied to the atomic physics, but also it can be applied to the information theory and even the information technologies, or some like communication technologies. So that's why it's so interesting, because nowadays everything is based on how we do the information processing. That's of course the very big application for the second quantum revolution is a quantum computer, so which nowadays is very hot. So basically, the second quantum revolution, I would say they want to utilize the properties of quantum mechanics, especially the quantum entanglement, quantum superposition, and quantum tunneling. So maybe I can briefly talk about the what do they mean when I say quantum, these different principles. So there are lots of different ways to describe or explain these different principles. But I would just use that to I would just use some simple ways to make everyone can know some sense. So the first principle is quantum entanglement. So I guess it's easy to understand. Just add what it means in words. So basically, you can think about that when you can think about that theory of the interaction of the atoms. So which means if you change the properties of one atoms, then the other properties of the atoms will change instantly. So these possibilities is very important because it can be used to enhance the security of the communication with what we call the QKD systems, and also in this way, since your data is transmitted by the protected cipher case, then you can use that entangled atoms to detect if someone has interfered with your the data transmission. And another principle is a quantum superposition. So this theory basically means for the atomic particles on the atomic particles, they can exist in multiple states simultaneously. So this is very mind-blowing. Based on this series, a very practical application is quantum computers, because for the digital computers nowadays they can only store data as bits, which is 1 or 0 as a binary number. But for the quantum computers, based on the superposition theory, you can use the qubits to store the information as 0, 1, or both at the same time. So this also creates a lot of infinite range of possibilities. The benefits would be that will allow the quantum computers can do some really incredibly fast simultaneously and parallel calculations. So that's why there are lots of people, physicists, they are so interested to develop practical quantum computers. So which definitely can help us to bring another angle for the model technologies. That's a very simple way to talk about this topic, and it's a quick introduction. Besides that, if we can have some improvement in the quantum technology overall, so there are some very interesting applications. I would say maybe I would summarize them as four major area applications. That's just my opinions, so you can find some different opinions in lots of articles. So I think for the quantum technologies, there will be some fundamental changes in the 4 different areas. So one is to definitely provide a more secure communications, and another is to of course we mentioned the more powerful and more reliable and incredible computing power, the computing machine. Then the third one, I would say it can also provide more accurate the quantum sensing, quantum imaging systems, which can be used in the lots of different sub-areas. And then the fourth one, I also think about the quantum technology can provide a much more reliable navigation and timing systems. That's yeah, it's really interesting. So I couldn't foresee, based on my knowledge, I couldn't tell like how far away we are going to have something practical for the applications, like long term or near term. But definitely, this revolution will be coming in the future, and it's really interesting about the uncertainty about how advanced the quantum application will come in. So yeah, it's a very good opportunity for us to watch and see, and I would be very honored to deliver this session to all you here. So we are very humbled to participate in this field. So would like to see how the future goes and how we can push this technology forward. So feel free to jump in the stage, everyone. If you want to particularly to talk about any theory or any sub area, I would like to share more about what I know. And also, I think Cecile, did a lot of research about the current industry, technologies, status with different companies and different leading research institutes. So I would also be excited to learn from Cecile and to see what's our approach nowadays. And also feel free to jump in the stage, everyone. I will pass mic to Cecile.
Thank you so much, Hera. I see someone raising his or her hand, but I cannot identify. Who can you see?
Welcome, Aaron.
Oh, thank you for having me here. Thank you.
So I am very excited. Of course, there's a lot of news about quantum news, but one of the biggest news that came, and I was surprised because I did not notice this before we organized this room, but this is some kind of news that is very close to my heart because about last year when Mark Jackson came here, he was also very sad about several experiments trying to say that they could not find any Majorana fermion, which is an exotic quasi-particle, which is very much needed in theory for some companies trying to think about using that particular technology to scale up quantum computing. And now, I'm very glad to see this news about Microsoft. So it says that, in a historic milestone, Azure Quantum demonstrates a possibility of trying to look for some other kind of qubit. So I would like to say a little bit about this news because it's all over in the past maybe 2 days, and I read about it only recently. So I think Microsoft has been going into this research for maybe they said that maybe it's about 20 years, but I noticed this research only in 2016, and usually in quantum computing, what we consider is about the fidelity, meaning to say they measure quantum volume. Is it good or not? Is it free of noise? And the problem about interference, has it been mitigated? Is it being solved? So 3 factors: the fidelity, the speed, and the size. Because more qubits we have, the better the quantum computer is. So yeah. In this case, as compared to other companies trying to develop quantum computing, Microsoft has been researching on using a different kind of technology, and they are considering using um, quantum braiding. And in 2016, well, I looked at um, several lectures of Leonard Susskind, talking about this theoretical study that they have about braiding, and it was so very interesting because Microsoft said no, unlike Google or other companies, we do not need to have so many qubits. We just need a fewer qubits, and the most important thing is that the kind of communication protocol that we do is just without noise, so that we are able to build an efficient quantum computer. So they were capitalizing on what you call the onion. And in physics, the onion is the type of quasi-particle that occurs only in two-dimensional systems with properties much less restricted than the two kinds of standard elementary particles, and these are the fermions and the bosons. If you will look at my Twitter, there is a meme there that I posted about onions, meaning to say, the fermion was saying, keep your distance, and the boson said, come on over, let's stick together. But the onion um, tries to adapt in all phases. So this is very important because they can shift phases, and therefore it brings out a new characteristic when you try to use it for quantum computing. So yeah, in this particular case, that's in the news that I put. So Microsoft quantum team reports observation of 30 microelectrons, um, topological gap in iridium, arsenide, aluminum heterostructures. So yeah, after a while, I just want to explain that this is just a simulation that they did now, but they are quite excited about it because they said that gives them some guide about the underlying physics on how to make a topological qubit. And yeah, of course, a topological qubit is very important to them because they had been waiting, for this to have some possibilities. But just imagine the amount of money that they've used, and they're waiting. And then last year, their hopes were flagged down because the exotic particle that they were waiting to have did not was disproven to exist. So I would just like to read a little bit or say a little bit about this news. Topological quantum computation is a route to hardware level fault tolerance, potentially enabling a quantum computing system with high fidelity qubits, fast gate operations, and a single module architecture. Meaning to say, as they were discussing, they were saying that what is the advantage of this and why? Why do they want to reach this? They were saying, the representatives of Microsoft was saying their main target for the use case of this quantum computing is for discovering new kinds of chemistry and also mitigation of climate change and healing of diseases. And they said that it will really help if there is really a scalable quantum computer because, of course, existing in a single module, meaning to say you do not need to put up several networks in order to come up with a result. And if why will quantum computing help us? Because we have a big problem and that it can be solved faster. For example, 1 month versus 50 years. So being confronted with this conditions that is an existential threat to humanity, they think that quantum computing can help us. So the fidelity, speed, and size of a topological qubit is controlled by a characteristic energy called topological gap. This path is only open if one can reliably produce a topological phase of matter and experimentally verify that the subcomponents of the qubit in a topological phase and ready for quantum information processing. Doing so is not trivial because topological phases are characterized by long-range entanglement of their ground states, which is not really accessible to conventional experimental probes. So they already made a theoretical paper, and I think last year they made a topological gap protocol on how to try to make this happen, and they this is a criterion for identifying the topological phase in quantum transport measurements. So topological superconducting wires have a Majorana zero mode at their ends. There is really a fermionic operator localized at each end of the wire, and this is analogous to the real fermionic wave equation constructed by Ettore Majorana in 1937. Well, he has an interesting story. You know, when he discovered this exotic particle, he disappeared a year after, so up to now he hasn't been found. So yeah, consequently, the two quantum states of opposite fermion parity that can only be measured through a phase-coherent probe coupled to both ends. In electrical measurements, the Majorana zero modes cause zero bias peaks in local conductance. However, this bound state disorder can also cause zero bias peaks. So yeah, I would just like to explain that I'm not an expert in this, but I just know that they tried to combine two kinds of materials in order to attain this phase. And what are these? They combined a semiconductor and a superconductor, and they used iridium arsenide, which is a semiconductor, and aluminum, which is a superconductor. So what is iridium arsenide? It is a semiconductor composed test the appearance of gray cubic crystals. It is used for the construction of cooled detectors. They have lower noise. So yeah, it was explained also in the article that they have to put this system in a temperature, the lowest temperature ever in the universe. So, and they use some kind of dilution refrigerator. So maybe in the future, some experts, can discuss about the technology underlying this. But I thought it's very important to share because this will create a paradigm shift. I think in the past, we had been talking about the problems in scaling up quantum computing. And if they become successful in trying to do the experimentation, I would like to say, number one, the paper that they shared here is still a preprint. This has not been reviewed yet and officially published. And number two, what they are talking about here is just a simulation. However, they said that in order to avoid bias, there are so many simulations that they did, and they had some non-Microsoft people try to assess the report that they had made. However, why are they inspired? Because this will try to create a new kind of physics condition that would give them a way to do experimentally to construct a topological qubit. And if and when they are able to do that in actual physical execution, there is a lot of hope about this project that the Microsoft has been spending for a long time, and there is a lot of hope also for maybe there is a race towards not only quantum supremacy, but for every quantum company who is investing a lot right now, there is a race as to who can create a quantum computer which has a lot of fidelity, speed, and size. So that is my news for now.
Yeah, this is a very interesting news. I think it came from today from Microsoft. Yeah, so I just did a quick look, but I didn't understand a lot of things. So I hope the experts in the room can educate me on that. I don't know too much about this topological qubit, and also I think in the field in overall, this approach is very controversial, and lots of physicists are debating if this is a feasible way to do the quantum computing. What I know is that back a few years ago, when the first time Microsoft proposed this idea, it's very hot. It was a very hot topic, so they proposed there would be a new physical matter. So they kind of want to use a semiconductor in conjunction with a strong magnetic field to get that topological physical matter, which they think this new compiled material can be used to realize the topological qubit. But I don't know how well they do it. This is still a puzzle to me. And I think my question is that even they can theoretically prove, like they can realize this topological qubit, but how do they control the fabrication? So that means, do we really have that kind of pioneer way to do the fabrication? That's the first question. And then the second question is that how do we grow the material required at the nanoscale? So which means, do we have the methods to create materials which may require some special growth techniques? So I think that's really questionable, at least based on what I'm understanding. So, and not to mention like how you control the cost and how you do the mass production. If you think about long term. So I think overall it's hard to control the accuracy, in the function and in the material in the fabrication. So this is a big question mark for me. But today's news, it seems like they think they can find a easy way solution to scale up the quantum computing. I didn't read that paper yet. But from the headline, they said they would bring us closer to the scalable quantum computing. The basic idea, I would say, they feel like based on the topological qubits. So you will have a strong control structures. So in that way, you will have an easier way to decrease the noise, which can get better fidelity of your qubits. So which can make your qubits more stable. So in that way, they feel like they can get a low error rate. So which is easier to do the error correction. That's what I read and learned from this news. So thanks for sharing, Cecile.
Also in my Twitter, I had posted just to show some history about this news, because I had been following this since 2016. There's an academic paper also in Nature, or an opinion paper in Nature, trying to tell Microsoft that they are attempting to build qubits out of particles that some scientists think might not even exist. So yeah, I saw John Perskill also repost the article about this news today, and he's very excited because, I remember he made a poem about onions maybe in 2012, and several other scientists have been talking about braiding and onions and exotic quasi particles. But he said, yeah, this is really, really good news. But I hope, that they are able to realize in actual experiment the physical implementation of this simulation. And I just want to say that this paper has not yet been formally published. So, but if this happens, this will really create a paradigm shift for um, to solve one of the problems as a one solution to scale up quantum computing. So yeah, that's my news for today. So yeah, I'd like to say hi to Hansen, who joined us here on stage. Hi, Hansen.
Hi, Cecile. Hi, Sierra.
Yeah, so we're just having some updates on what's happening in quantum tech. So yeah, I'm sharing another news in a minute. I will just change the pin link. If you have no more comments, does anyone has comments from the audience or from the stage? Or
yeah, any thoughts on this, Hansen?
Not so far. I mean, I read about the quantum topological quantum computing computers and topological insulators, but I haven't dig deep into it yet.
So okay, I will change. I will go to another news in a minute.
Maybe 1 minute. I can share a link, so which deeply related to this topic. But
sure.
Also, I didn't know too much about this topic. But I feel this this is a very old reference I read a long time ago. It's really helpful to understand what is topological qubits and what Microsoft is trying to do. Yeah, so I'm not sure how much I still remember, but yeah, it's there are a lot of information. So I would encourage you to save this link to read about later, because there are really some good points. Yeah, so what how to say, so like yeah, so basically I think the topological qubits yeah, so what Microsoft is trying to do, they are basically to search this Majorana qubits, if I pronounce right. So basically I think what they are trying to do is they want to encode a single bit of information in the multiple quasi particles, and also based on their theory, which developed by the Microsoft engineers. So they think by using this kind of design, the quantum information will stay longer and more stable, which means you have less chance to lose this kind of information. And even more, if you move this information with the different materials, they claim the information can be immune to the local environmental noise, which is very important if that's true, because that means, basically you will have very less errors if you can get this Majorana qubits. But what's the difference is that for the current approach, like this article mentioned for the Google and IBM, so basically they store the information in the single localized object. But for the Microsoft's approach, they will store the information in the multiple quiz particles, which is the multiple particles at the same time. So I still don't know too much about this, but based on what they claimed, it's very interesting. It's if that can be achieved, so which means you don't need the same type of error correction as the superconducting qubits, because fundamentally you would have less error, and also it will be easier to make like a large number of the working qubits quantum computers with the topological qubits. So that would be something fundamentally different for the for the topological approach. But still, this is very controversial, I would say. But I'm glad to see the Microsoft finally announced the new development after almost like 5 years of silence, I would say, at least not public. So so it would be interesting to see if there is anything new. So I would definitely to read more about this approach, and hopefully I can have some more insights. But if you are new to the topological qubits, I would definitely recommend this. The link I shared. As I read a lot about the papers and articles in these topics, but I feel this is the best reference so far. Thank you. I'll pass the mic to Cecile or Hansen if you want to comment.
Thank you, Shira. I hope you will post that also for the reference of the audience. We will post that in the Quantum Photonics Twitter account so that they can look at the history of this, because maybe in the future we'll talk about this when somebody who's working in the field will come to visit us in this club. I think it's really, really interesting. So shall I proceed to the next news? Is there any question or comment from the audience about this? Because if not, I will go to the next news. Okay, so I will change the pin. Because as you see, when there is an exponential growth about a technology, or there is disruptive innovation, what happens is that the one who brings the technology changes the rules of the game. And so, just like what happened when we had the drones and we had driverless cars, we have even Uber and the other disruptive technologies that came in, and we were just trying to use it suddenly, and it became a part of our lives. Even for blockchain, for instance, if you will ask people what laws will apply to this, and even when we had these drones, there was a lot of confusion as to what will govern the implementation and the massive use of this. So I think this is also very important for when we have this technology, and of course we don't have this actual quantum computing yet, I mean to a massive scale. So they were talking about this. So in this article, an Albany law professor says the scholars, industry leaders, and government regulators need to quantum internet regulations and discussions should be informed by the lessons of the past. So this person who was recently named heavily by the National Science Foundation Center for Quantum Networks, legislators and others will need a firmer grasp on past technology regulation debates to make informed decisions when quantum computers become commonplace. While it remains difficult to confidently predict how and when quantum technology advancements will take shape in the coming years, or the legal and cybersecurity concerns that may come with the advent of quantum networks, policymakers can expect talks to sound like those when the internet just emerged in the 1990s. To get a jump on legal discussions about quantum computers, heavily predicted an interdisciplinary field of quantum law will emerge alongside the technology, drawing much of its wisdom from past lessons in tech history. He said that he and his colleagues act as trailblazers for the emerging discipline, which aims to help build understanding of the technology among law students and lawmakers, as well as its potential social implications. It remains to be seen what types of law school courses might comprise quantum law, but the idea is that students, and especially those responsible for future regulations, will need to remain informed in order to safely navigate changes happening in quantum technology. So Heverly said that the field will look to build communities of scholars, industry leaders, and government regulators with hopes of encouraging them to talk about these issues in a way that makes sense. So I think several years ago when Juichi Ito was still the executive director of MIT Media Lab, he was having a joint program, a course with the Harvard Law, trying to discuss on how the new technologies will be treated and how will they try to do legislations and regulations about these particular technologies that we have. So I just read in some of the articles that a lot of people involved in like quantum machine learning and of course quantum computing and other quantum technologies which are emerging are very happy because there is I think the schools will already put courses about anything quantum, and also there's gonna be a graduate school for quantum computing and quantum machine learning. So gradually, this industry, of course, will be needing more people to work. There will be new skills needed. And what I understand, for example, about Cambridge Quantum Computing, which merged with Honeywell and made Quantinuum, and I think they also have Strange Works, which is doing this, trying to help us about preventing, quantum noise. So they are putting up. I think it's in Colorado. They're putting up a plant in somewhere in an obscure area, and of course, that plant. Whenever you put something, it's gonna build a new industry, a new community, and a new need. And also, in that case, who will work for them in the future? So that's why I think they're putting up some training center or school in order that people will have the skills to deal with what they have, because it's a combination of, their foundry for quantum computing and also at the same time doing the software for that. So, of course, they have to involve people in the community. So, as you see, there is going to be a micro and macro change in even, the way we live. If this industry that of quantum computing, be it software or hardware, there are dynamics in economics and political systems that they bring about. So, I think this news for me is very, very important, because instead of waiting that technology technology already confronts us and tries to knock on our heads and gives us a problem, it's better also to anticipate what kind of regulations or law that we're going to use about it. And I just remembered something in relation to that. This story about NFTs and what's also happening in the metaverse. There's a lot of question now as who's gonna own, some intellectual property rights about certain NFTs maybe that we have, and what regulation should be done. So yeah, it's a similar story to any kind of new technology that would suddenly come and affect our lives. Yeah. So, any comment?
Yeah, I'm always wary about any new regulations. In most cases, statistically speaking, new regulation is always a bad thing. And the technology. I mean, I think there's saying in India, the reason why their software industry boomed was that the government was too behind, didn't know what to do with it. Had they been more aware and alert, there probably wouldn't be an IT industry in India.
Thanks, Hansen. Yeah, so if no one has questions, I'll go to the next news that I will share.
I can share a link here.
Go ahead,
so
please.
Since very related to this topic, it's also old reference, old articles I read a long time ago. It's very interesting to hear about the quantum law. Basically in this paper, it's it's just a concern about the quantum technologies threat to the current cybersecurity and also the encryption structures. If you know the current the encryption structures, which is called ISA, so particularly for sending some sensitive data over the internet, it's based on the 2048-bit numbers, some experts they estimate a quantum computer would need as large as 17 million qubits to break that encryption. But nowadays we have the largest quantum computer would be IBM's 53 qubits system. That still take a long time to break our today's encryption. But why we are worried about this? Because the pace of the quantum research will continue to accelerate. There is a very interesting paper, so which I shared here. So they published this work in the MIT Technology Review, and they demonstrated that if we have 20 million qubits computer that can easily break 2048-bit number only in 8 hours. So this paper actually what they demonstrated means we have our continued breakthroughs will keep pushing the timeline up. So that's the reason why we have to think about the security issue and also our like the encryption threat based on the quantum technologies. So it's very important to come up something like the quantum law. That's my take on. Thanks, Cecile.
Yeah, thank you. I remember we had a room with Rishi about the quantum death of the blockchain last time, and we opened a discussion about that. So,
is 2048 the number of bits, or is it the memory?
Can you please repeat what you said? I did not hear you well.
Is 2048 the number of bits, or is it the memory that is being addressed?
Death of the blockchain last time, and we opened a discussion about that. So,
is 2048 the number of bits, or is it the memory?
Can you please repeat what you said? I did not hear you well.
Is 2048 the number of bits, or is it the memory that is being addressed?
It's a number of bits. So you can Google search what is RSA encryption, which we are using nowadays for the common encryption technologies.
I think it's very important, to think forward. And anyway, Shara, do you have something to add or any comment?
I would like to see what you are talking in the future, like the next years. But for this thread, so actually there is a for the U.S. side, there is a U.S. National Institute of Standards and Technologies, so which is called NIST. They actually propose lots of potential methods for this kind of threats. So you can easily search the post-quantum sorry, what is that? What? Sorry, I need to think about that. The post-quantum, cryptography. So the PQC. So they propose lots of the very interesting proposals. They have a very, I can share the link later. So they have I cannot remember, but at least 50 methods to deal with this cybersecurity issue. I don't know too much, but from the theory point, I would say a very promising method is the quantum key contribution. So of course you can, that's a basic principle of quantum mechanics. You can use the key to transfer the information between the data, so which cannot be easily hacked. But I would share the link later about the NIST website.
These billions of qubits that go into making a quantum computer, do they comprise of the material that goes into the semi-processors, microprocessors? So these qubits, do they, go into the making of this microprocessors? That's my question. Hello?
Yeah. Thanks for the question. I'm not sure if I got you, but maybe I mislead you. Why I talked before. So actually, this is only a theoretical simulation to about how the quantum computer can break the encryption. It doesn't mean we have like this much qubits, but they claim we have to have like 20 million qubits to break our current ISA encryption system, and that only need 8 hours. Yeah, before they with our old technologies, so they said we have to use like 70 million 70 million qubits, so which which you still need a long time, but with the with the technology development, so they did another simulation, so they claim we only need 20 millions in 8 hours instead of like 70 million qubits. So that's how like the physicists and the scientists, they address this issue. So to like advise the government or some other institutions to address the importance and urgency of the deal with this threat. So that's why I mentioned the NIST. So they host they host the different conference to deal with this issue, and they have a very specialized committee members. So they have the different very interesting proposals. I think I also read about they open to the public to ask for the proposal to solve these issues, and then they did like a committee review, and they finalize some different approach, and also they advise the approach to the U.S. government in the future to deal with this kind of issues. I hope that's clear.
No, see, I mean, I just want to understand when they say, right? I mean, I went to this article that you have pinned in this wall. I mean, it says billions of qubits go into making of a quantum computer. So, what does that mean? So, where are these billions of qubits? Where do they go into? I hope you got my question.
Are you asking about the Mariana particle quantum computer, the topological quantum computer?
No, 1 second. I'll just pinpoint you the sentence there. 1 second.
Is it indicated in the article that there are millions of qubits? Trying to take a look at it now, but I couldn't find it, so maybe you can try to enlighten us about that.
I'm not sure if I got the various question, but
hold on a second. Let me just read this out. In 2015, researchers estimated that a quantum computer would need 1 billion qubits to do the job reliably. That's significantly more than the 70 qubits in today's state-of-the-art quantum computers. So, I mean, where are these billions of qubits? No, where do they go into? Like, I mean.
So like there is not like practical system. I mean, there is no physical system. It's just a simulation. So they base on their simulation, and they claimed you need like 20 million qubits computer, but they didn't have a physical one.
Yeah, I think, given the conditions that were there during the time, of course, they estimated that to be billions of qubits, but actually, since that time, there are a lot of studies that you would need to consider in order to scale up the and not only the size. I don't know if you hear me because I see a red mark in my phone. So that's why they are trying to measure also quantum volume, and they are trying to also reduce the quantum to have better quantum error correction. And based upon the news that I gave earlier about Microsoft trying to build topological qubits, they wanted to make a quantum computer which is based on that, because they would not need so much qubits as other companies who are building quantum computers in order to come up with a result, a desired result that they have, because this has lesser noise, and that the interaction of the quasi particles that they use when they do this braiding um, is giving a better fidelity to quantum computing. So yeah, since that article was I think 2019, of course, we still haven't discovered so much about how to scale up. It's still a big problem, but I think many steps were done after that to study on how to scale up, because, failures had happened in experiments and people are spending a lot of money. So I think there are changes in the opinion also of the scientists on how to solve this problem. Yeah, so anyway, that's how I understood about the what was said there in the article. But I have to read it again because I just saw that only now. So shall I go to the next news, Shara?
Yeah, go ahead. I'm excited to see what you will share next.
Well, this is just popular news. So anyway, I will share it. Yeah.
Hello?
Sorry, I was on mute. So this is a NASA-funded experiment um, which tries to try to use quantum computing to mitigate how they are able to do their experiments and do communication with us here on Earth and in other parts wherever their experiment takes them. So um, they are among those institutions who try to um, go seriously into testing quantum computing in order that they will improve the science that they have. Because, of course, I saw car companies now trying to invest into that. Also, transportation companies which are doing these deliveries of cargoes are already starting to invest in quantum computing. So yeah, I'd like to read just a little bit about this tiny experiment launching to the International Space Station later this year could set the stage technology demonstration. So it's small, it's milk carton size. We'll test two communication technologies in the harsh environment of space. So quantum computers hold the promise of operating millions of times faster than conventional computers, and distributed quantum sensors may lead to new understandings of Earth and our place in the universe by measuring small changes in gravity. But for quantum computers or quantum sensors to communicate, they will require a dedicated communications network. A key component of this network will be space nodes that can receive and transmit quantum data to and fro the ground via the free space optical communications. So this project sets out to prove the viability of these technologies that could enable orbiting nodes to securely connect quantum transmitters and receivers over long distances. To do that, these nodes will need to produce and detect pairs of entangled photons, eventually transmitting such photons to quantum computers on the ground could provide the foundation of quantum cloud computing. That means to exchange and process quantum data regardless of where the computers are located. So, they're talking about quantum cloud computing. And of course, now we have simulators which you can find on the cloud. So, of course, these are not the actual quantum computers, but actually, companies are starting to put it on open source to some people who would like to understand quantum machine learning because they feel that if they are able to scale up quantum computing already, and there will be no people who would try to understand how to use quantum machine learning, it will be a big problem. So they try to develop this technology, the use of quantum machine learning to as many as possible so that just in case they are able to scale up, people will be familiar with the system, and in that process they will already, with the small qubits that we have and trying to bring the simulation in the cloud, people will find the use cases and will develop protocols to do that. So but I think that in the future maybe we can also discuss how they did this quantum computing in space technology, especially because they're talking about encryption. They need photonics here because they're talking about entangled photons. So, but they will be using the cloud as well. So, quantum sensors are also very important because they sense and they bring communicate whatever they sense in their environment, and give it as an input to the computation that we will have. So, yeah, that's my news.
Great news. So this is a perfect example about quantum communication and the distributed the quantum sensors. So so it's basically applies to the quantum key distribution, and also utilize the entangled photon pairs to store the information and transmit that information with key. It's very interesting. So I would like to see how they proceed in the future.
Yeah. Well, we will just have to watch out. What's gonna happen to that next. But if they are able to make good use of that, then it will help a lot about. It will bring a lot of science also to us. So yeah. Any questions or comments about this? Because if not, I will go to another news. Yeah, so I'm going to change the PTR here. Pin link. So I haven't read that well, but I don't know. If you would like to go to the link, can you tell me who has the highest budget, at least in 2022? What country has the highest budget for quantum computing?
Before I click that link, I would say it's like Europe on the US. That's my guess.
Yeah, I think so too. But anyway, I would like to go to check the link again as to who has the biggest budget. So yeah, I saw another article talking about more countries who have this budget. But anyway, in this article that we have now, they just talked about China, USA, France, Japan, South Korea, India, and Germany. So, yeah, quantum computing tends to be one of the major disruptive technologies in the near future, with the promise to simulate complex interactions of atomic structures through smart quantum computing. So there is a race, of course, not only among companies, but as it is an important technology, also for countries, for governments, for defense, and of course, whatever we discover will also try to translate to, how much power we will have as a country if we have a particular technology that we control and we have the most superior on that line. So, well, in this article, they talked. The U.S. is having a budget of which is going to be spread on a 5-year investment of $1.2 billion in quantum information research. So, yeah, but it's going to be distributed over 5 years, so it's going to spread. So the government of China announced the funding of a multi-billion-dollar quantum computing mega project with the goal of making important quantum discoveries by 2030. It did not say how much budget they have. Maybe they have a big budget. It pledged billions of dollars to fund the establishment of a Chinese National Laboratory for Quantum Information Sciences. So France has announced a 5-year, 1.8 billion euro strategy to boost research in quantum technologies, particularly in quantum computers, bringing public funding in the field from 60 million euros to 200 million euros per year, putting France a third place behind China and US in terms of quantum funding. So maybe the US is number 1, number 2 is China, and France is number 3, or China is number 1, the US is number 2, and France is number 3. So for the next one is Japan. For the fiscal year beginning 2020, Japan's government allotted 30 billion yen, which is about $276 million for quantum research, doubling the previous year's proposal. So this technology would focus on a government-funded moonshot R&D initiative worth a total of 100 billion yen. The next one is South Korea. The new quantum computing research in South Korea will involve a 5-year investment of a Korean won 44.5 billion, which is about 39.7 million US dollars to create core quantum computing technologies. So then the next one is India. I don't know how to translate their money to dollars, but anyway, it's among the list. Maybe it's number 6. And then Germany is the next one. Germany will spend about 2 billion euros to assist the development of its first quantum computer and related technology. It will be supported by the Science Ministry. So yeah, maybe I saw other countries. I think even Thailand was included, and other European countries in that list. But maybe these are the top 5 that are having some budget and highlighted investment into quantum computing.
Yes, still, I think I said that in the back channel. I'm very surprised to see the China is here, because as far as I know, China, they did a lot of investment in the quantum communication, but I don't think they are doing too much about quantum computing. But maybe I'm wrong, so I will do more research regarding to this.
Yeah, so a lot of I think last year and this year is a lot of people are trying to leverage on investment in quantum computing because if you notice, Shara, remember there is a merger of Cambridge Quantum Computing, which is doing software, and also Honeywell, which is doing hardware. And in the middle of that, they made a company which is doing quantum error correction. And I think they also made another company called StrangeWorks, which is having this algorithm to, I think they're selling it to the finance industry. And I think a chemical industry also, which is already some kind of problems, if hacking quantum computing is able to hack into the security for cybersecurity. So, and I think there was some kind of a joint project by Azure and I think even IBM. Um, and of course, Azure is with Microsoft, but I'm surprised that some companies are joining hands to make bigger. And also, Rigetti is already had became a public corporation. They went to the stock market because they got a SPAC investment. So everybody is trying to expand, and I think Shara, you told me about Alice and Bob. Can you tell us about this company because I'm interested in the name? I know maybe you are not a fan, but can you tell us about Alice and Bob?
Yeah, I think they are very. They are also a company doing the quantum, but they didn't. They didn't have something new, I would say, but they want to build a universal and error-free quantum computers. So they want to solve some industry problems, especially the hardest problem. But I didn't see they have too many news on too many project or roadmap updates. So still a very quite new company. Yeah, I think this still is a startup. I think they founded like very recently, like 2020, if I remember correctly. But they claim they did they really got some funding. Their approach, not approach, their vision is very good. So they want to find a perfect qubit. So basically, how to say? So basically, so if you think about the classical computing, that's like you will have a bit flip type error, so which which give you like 0 to 1 or 1 to 0. But in the quantum computing, so you will have, besides that, you will also have a phase flip error, so which means the qubits can become like positive, negative, and vice versa. So, but Alice, Bob, so they kind of also doing the the superconducting qubits, or they called that in a very interesting way called Schrodinger's qubits, or they call that as cat qubits. But basically, that's the same thing. It's similar than the superconducting qubits, but they claim their approach is their like cat qubits are less sensitive to the errors than those development by the IBM or Google using the superconducting qubits. Yeah, but I actually didn't see too much updates since they propose that vision. but their name is their name was very interesting. So and also they named the qubits they try to development called Schrodinger's cat qubits. So that's why they called Alice and Bob. And also they try to solve they try to build a quantum communication network, and they want to solve the hardest problem using their system. If I remember correctly, they got a few rounds of funding, and they claim they will deliver first structure to demonstrate their perfect qubits, which is cat qubits on Schrodinger's qubits by 2023. Which is next year. So definitely I will keep an eye on that. But so far they didn't have anything in public. But based on what they delivered in the public press release, so they would want to do something like less error or even towards error-free quantum computer using their perfect the cat qubits. So that's what I know so far. So hopefully that can give you some ideas about their approach.
Yeah, I will try to follow them also because I like their name, Alice and Bob. So yeah, I think I'm going to my last news today. So yeah, I will just change the pin here. Yeah, so yeah, I still have a lot of news, but I think this is going to be my last news for today about quantum. So Pascal and Aramco. Aramco is the biggest company actually in the world now. They deal with oil and energy. So I think Pascal is a French company. They are a developer of neutral atom-based quantum technology, and Aramco announced the signing of an MOU to collaborate on quantum computing capabilities and applications in the energy sector. Objectives include accelerating the design and development of quantum-based machine learning models, as well as identifying and advancing other use cases for the technology across Saudi Aramco value chain. And to that end, both companies plan to explore ways for collaborating and cultivating quantum information sciences ecosystem in the Kingdom of Saudi Arabia. So quantum computing can be used to address a wide range of upstream, midstream, and downstream challenges in the oil and gas industry, including network optimization and management, reaction network generation, and refinery linear programming. So the collaboration will explore potential applications for quantum computing and artificial intelligence in these areas as well. So as part of the project, Pascal will provide both its quantum expertise and platform to develop new use cases, and the companies will explore applicability and benefit of augmenting Aramco's training programs with Pascal's quantum technologies as part of their joint efforts. So Aramco is focused on pioneering the use of quantum computing in the energy sector, positioning itself as an early beneficiary of quantum advantage over classical computers. Pascal aims to establish operations in the Middle East and grow its business in Saudi Arabia and across the region. So yeah, this is a promising future for Pascal, but at the same time also, Pascal builds quantum computers from ordered neutral atoms in 2D and 3D arrays. Actually, I have to read up on this because I don't understand this technology well, but anyway, they think that with the goal of bringing a practical quantum advantage to its customers in addressing real world problems, especially in quantum simulation and optimization. And Aramco is a global integrated energy and chemicals company driven to the belief that energy is an opportunity from producing approximately 1 in every 8 barrels of the world's oil supply to develop new energy technologies. Their global team is dedicated to creating impact in what they do. So, yeah, I'm familiar about Aramco, and of course, they are all over the world, and they have also a value supply chain. And then since I'm also working in AI Green, bigger dimension in all their supply chain, and they even have a chemical company. So yeah, they are among the first adapters and are aggressively investing in quantum computing. And who knows, just like Nvidia, who started out from using this their hardware for gaming, and then it became a tool for computer vision, and now they're becoming an AI company. And yeah, they're manufacturing some chips and designing some chips of their own. So there are evolutions as to what these big conglomerates are doing. So maybe since they have the money and they need it for internal operations in their company, Aramco is investing highly on quantum computing. And if they are able to play their games well, maybe we will be surprised to see that in the future Aramco has also become a powerful quantum computing company. Yeah.
Yeah, that's a beautiful share. So definitely there are lots of exciting quantum computing applications we can watch out. So the quantum so there are like as you just mentioned, like the artificial intelligence, and also here they talk about the financial modeling, and before earlier we also talk about the cybersecurity. So these are very significant areas can be harnessed by the quantum computing technologies. And also there are some other areas like we didn't touch on today, but we can definitely revisit them in another room. So like the drug development, on the traffic optimization, on the some electronic material discovery, or even some quantum simulation, like the weather forecasting and the climate change forecasting. So there are a lot of things to talk about in this field. So today we just touch base on some basic theory and some the state of art status in the field, in the industry, in the field, and also in the academia. But this is a fast growing field, so we can regularly revisit them, and hopefully we can see some more significant breakthroughs in the near future. Yes, thank you, Cecile, for doing this session. It's a really great discussion.
Thank you, Shara, also for explaining the technology to us. So we hope, to have more discussion regarding this quantum computing and quantum technology in the future, because it has become a very, very relevant, and a lot of money is being invested by different businesses, different categories of businesses and even governments on this. So it will really affect our lives, because the new investments, which are big, is building up new communities and new use cases. So we are going to revolve about it and around it. So yeah, we look forward to these discussions. Also in the future, actually, I have other news on quantum computing and also other quantum news, but we shall reserve that for next time because there are technical discussions also involved about that since there are new papers which came recently. So yeah, maybe for next time we will do that. So yeah, shall we already? Do you have announcements to make, or shall we call? I'll call Darcel up, and maybe you, if you have announcements to make or comments, yeah. I'll give the mic back to you first, Chair.
Yeah, so thanks, Cecile. It's a wonderful discussion. So we can revisit this topic again, as there are so much to talk about. And also in the future, this week we have some very interesting guest speakers sessions lined up. So if you are new to Quantum Photonics Club, please feel free to give us a follow, and then you can see all the interesting rooms topics in our club page. So yeah, so thanks everyone for joining the discussion and listening and giving us the support. So I'll see you very soon. I give mic to Jocelyn. Welcome to the stage.
Thank you so much. I'm just jealous that Dazzle was invited up, so I came up as well to help close the room out.
Well, you are so sweet, Jocelyn. Yeah, do you like to count down with us? Yeah, just jump on the stage.
Thanks.
Yeah, we like to hear about your voice.
Thank you.
Yeah. So.
Are we ready?
Yes, we are.
That's
I would like to announce the coming rooms first. Just a minute. So, yeah, thank you, Frank, for coming on stage as well. So, please support us because tomorrow, for the first time, Quantum Photonics will have some kind of networking because we are a community and we're trying to build a community, for all of us, in order that we will learn and support each other. So we will have a networking room tomorrow, and we will also be calling for crowdsourcing. In whatever way you can volunteer to make the community better. Maybe you have a speaker that you can recommend, or you can do a room here in Quantum Photonics, or because as of now, we realized maybe about 2 weeks ago that we're the biggest quantum group here in Clubhouse so far, and we hope that you will help us by trying to invite maybe even just 5 of your friends to be members of Quantum Photonics because we're nearing the 10,000 mark, and we had been growing so fast in the past weeks. Surprisingly. So we hope to reach the 10,000 mark because we are going to have our anniversary. I wasn't here yet, but it's Quantum Photonics is going to have its anniversary towards the last week of April, and we're going to have some events here and invite more special speakers. And so, if you have suggestions, we will, open up the forum because you are very important to us, and we know that you can contribute a lot to this community that we are building. So please be here to help us network tomorrow. And anyway, please invite your friends. We need your help to grow the membership here in Quantum Photonics. Yeah, so that's all I would like to say. I pass the mic to Shara first before also the other rooms. Just look at the next rooms that we will have. Tomorrow it's a networking and crowdsourcing day, and then on the next day we have a room. There is a speaker who's going to talk on how they were able to reverse aging in a super centenarian organoid, which might lead, to breakthroughs in the future about trying to reverse aging, not only stopping but reversing aging. And then, also we will be having a room about the future of cities and using decentralized protocols to be able to bring in primary health care. And on Saturday evening, we're going to talk a little bit about transhumanism. If you remember Chris Armstrong, who came here before as a pre-party for Sultan, he talks lightly about transhumanism, but of course, we will also talk about that and the technologies that are being associated with transhumanism. And usually, anyway, these are the technologies that we already have now. So next week there are going to be also interesting rooms. Just please check it out. We have, I think, Shara has invited someone to talk about quantum machine learning, and I invited also someone who's gonna talk about geometry and the ADS-CFT. And of course, they will say, "Are we in a hologram?" So there are physicists from Sweden who's going to talk about their paper on this. So just please check out, the club announcements as to the schedule. And anyway, hope to see you here tomorrow. Shara, I give the mic to you.
Frank, do you have any questions today?
Yes, thanks, Varun. Thanks, Jocelyn, Cecile, Frank, and everyone in the audience. So thanks for all the great support, great inspiration, and also the great discussion here. So that's our biggest motivation to keep this room going and going. So I hope we can continue to do this since it's very interesting and make my life so much better, since I can always think about some fascinating topics. So I hope we can do something good and harm to your life and bring some joy and inspiration and some new knowledge to you. So again, thanks everyone. I really appreciate your support. That means a lot. And always appreciate the great team members like Cecile and our other moderators team here to help out. So I pass the mic to the stage and maybe Cecile, and we will see all of you soon in our future rooms.
If I may add, we had a lovely room last night, and what I love about that room is that we brought in a lot of lay people, not just scientists, but just people who are interested in learning more about Einstein and Hawkins. So it'd be nice if we have more rooms like that, where there was a nice balance for the experts and the lay people.
Jocelyn, please tell us, later, so we can also, the personalities or scientists who might be good inspirations for similar rooms like we had. And we hear you, so and we will consider that. Darcel?
Thank you both. You just phenomenal, extraordinary people. You give so much of your time, and not just here on the app, but also, you give to people like me. So I appreciate your caring nature, your compassion, and your empathy. Thank you so much.
Thanks, Jocelyn. That's beautiful.
Yeah, that was beautiful. And a great room, Cecile and Sierra. All right, we're going to start with lucky number 7. Is everybody ready?
Ready.
Here we go. 7. Route 66.
6.
5.
5.
4. 33 and a third. 2. Cecile, Sierra, Varun, Jocelyn, Frank, you're all number 1. Call it.
So are you.
Wow.
Thank you.
Thank you.
Good night, everyone.
Have good dreams.
See you tomorrow.
Bye-bye.
Take care.